In this lesson, we're going to look at some of the crazier formulas that the Regents has to offer. Now, even though that sounds intimidating, it's kind of nice to have these formulas because in the questions, they're always going to provide us with a formula and they're going to provide us with the pieces to plug in. We just have to make sure we read through carefully and plug in the right parts to the right variable. So if I read through this first question, after heating up in a teapot, a cup of hot water is poured at a temperature of 205 degrees Fahrenheit. The cup sits to cool in a room at a temperature of 67 degrees Fahrenheit. Newton's law of cooling explains that the temperature of the cup of water will decrease proportionally to the difference between the temperature of the water and the temperature of the room, as given by the formula below, where T of T is the temperature of the object after a time of T hours has elapsed. T of A is the ambient temperature, the temperature of the surroundings, assumed to be constant and not impacted by the cooling process. T naught is the initial temperature of the object, and K is the decay constant. Now, if the value of decay constant is 0.084, write a function in terms of time t. Well, so remember, this part already tells me that t should still be in this function, but everything else we're going to plug into. So if I look, first one was T of T. If that's the temperature of the object after T hours has elapsed, let's see. We don't know how many hours is going to actually pass, but if I go through here, that's what we're trying to find out. So we can't plug into that one just yet. If I look at T of A is the ambient temperature, the temperature of the surroundings. That's going to be this room temperature of 67 degrees Fahrenheit. My initial amount is how much it came out as. So that's the temperature of when it comes out of that teapot to start. And K, we were just given in our part here. So when I go to plug in, T of T equals, T of A we said was 67 plus, we had the initial amount, subtract that constant room, don't forget that's a negative, and then we'll have our 0.084 T. And I could leave it just like that. Now I could always go in and simplify the 205, subtract the 67, but if it just asks me for a function, this would totally count for full credit. Now we are going to go in and figure out the Fahrenheit temperature of the cup of water to the nearest degree after 4.5 minutes passes. That being said, we're just going to plug that piece in for T. Now remember, everything here can just be plugged into the calculator as long as you're careful. 67 plus parenthesis 205 minus 67. E, remember we learned yesterday, that is not a variable we're plugging into. E is Euler's number. That is a button on the calculator that we're going to plug in and raise everything in there. So pause the video and make sure you're practicing with your calculator and just plug that in for a moment and see what we get. Welcome back. So if you plugged it in correctly, you should end up with 161.5618091. And when we round that to the nearest degree, we get 162 degrees. So that is our current temperature of the water after 4.5 minutes has passed. All right, we're going to do the same thing again in number 2. So here in number 2, we have Kayla needs $30,000 for a down payment on a house she plans to purchase in 8 years. She decides to invest in a savings account, which gets 3.5% interest compounded at the end of each year. Assume she makes the same deposit on January 1st each of the 8 years and makes no other deposits or withdrawals through the year. Use the formula A equals D over R, parenthesis, 1 plus R to the T minus 1, where A is the amount of money in the account after T years, D is the number of dollars invested at the beginning of each year, and R is the annual interest rate of the account. How much money should Kayla put into the account at the beginning of each year to reach her goal? Okay, so when I go through this here, I'm going to kind of take a moment and target all of those pieces again. So we know that A is the amount of money in the account after T years. So T years, we got 8 years, and A is the amount of money in the account. We need $30,000 for this down payment. D is the number she's investing. So when we read through that, D is that number of dollars invested at the beginning of each year. That's kind of how much she's starting with. So that's how much we want to know. That's what we're looking for here. And R is the annual interest rate of the account. So those are our pieces. Okay, so I've highlighted those parts first, and then we can actually just take our formula and plug right in. 30,000 equals, we don't know what D is, that's what we're trying to find out. So D over R, remember it's percent, so we're going to change that to 0.035. 1 plus that 0.035 raised to the T, we said was 8 minus 1. And now we're going to work our way backwards to solve. So that being said, I would plug everything into the formula here. So we have 30,000. I'm going to go ahead and plug this into the calculator. That 30,000 is still there. We can't do anything with D just yet. But everything in here, I'm going to take a moment and plug that into my calculator just as is. So I plug that into my calculator. I get to 0.316809037. Now, in my calculator again, I'm going to divide that number from both sides. So remember, I would just use the calculator as I go in here. You don't have to write out all the digits, but we just want to avoid rounding too soon. I would keep like maybe 5 decimal places just to be safe. But I'm going to take 30,000 and divide just by using my calculator into that. So we end up with 94,694.26846. It's equal to D over 0.035. And that last thing here is we're going to take this 0.35 and multiply it from both sides so we can cancel it out on this side. Multiply it here on my left. So I'm going to take that number times 0.035. And we end up with 3,314.299396. And it's how much money should she put in? Remember, it's money, so I would round it to the nearest hundredth. So 3,314.30. Okay, so if money doesn't tell us where to round to, we just go with what money would actually be at. Okay. All right, one more problem. We have this monthly mortgage payments and we have the formula that's given. Everything's kind of brought down for us here. R is our interest rate. We're talking about a 20-year mortgage. So we got to be careful here. There's nothing for time. Instead, if it's a 20-year mortgage and it's a number of monthly payments, we're going to get 240 there. We're trying to linear set how much money the banks would need to borrow in order to have a monthly payment of 720. And we need to see we're trying to see how much money they would need to borrow. So we don't have P. That's what we're solving for in this case. So pause the video and try plugging it in on your own here, and then we'll check our answers at the end. Welcome back. So you had all the pieces to plug in, so you should have gotten that black part. 720 is equal to P. The rate would be 0.048 over 12. 1 plus 0.048 over 12, and n is 240, so we plug that in, all over 1 plus 0.048 over 12 raised to 240 minus 1. Since p is multiplied to all of that, I'm just plugging it all into the calculator. So as long as I'm really careful and using my alpha y equals and my parentheses to make sure I have everything raised to the right part, I can kind of skip ahead and plug this all in and cancel that out. So I'm taking 720 divided by that whole long piece. When I do that, I should end up with 110,947.1781. And remember, we're rounding to the nearest cent and it's money. So we're looking at 110,947.18. Now, you could do it step by step and plug that all into the calculator. As long as you end up with the same answer that I have here, either way is totally fine. But I would show that you plug in and then show how you go from there and try to do your best to avoid rounding anything till the end, so that way you're not off by a couple cents. Okay? All right. Thank you very much for watching. Have a good one.